Welcome to today's webinar with SCA and Dr. Steve Sonnenberg on exploring for Mudrock reservoirs, what we think we know. Before we start today's webinar, we'd like to ask a few questions about the demographics of the group. So we have some polling questions that we will share with you. To begin with, what's your primary discipline? So this will take us a few minutes to bring in these answers. We have people still logging in. Looks like most of you have voted, and we have a very strong component of geoscientists. So looks like 78% of you are geoscientists, 12% petroleum engineering, and a few in the other category, petrophysics and other. So our second polling question is related to how many years of full-time experience do you have in the oil and gas industry. So we're distributing this poll. We're getting some answers now. As those of you are starting to vote, it looks like we have a very good distribution. There's a few people in all of the categories. It looks like most of you have voted, so I'll go ahead and close those polling questions and share the results. We have 40% or over 30 years, and the next largest is in the 1 to 10 year range. So it looks like we have a very bimodal distribution. So again, today's webinar is exploring for Mudrock reservoirs, what we think we know, with Dr. Steve Sonnenberg. And Dr. Sonnenberg is a professor at Colorado School of Mines. He holds the Charles Boettcher Distinguished Chair in Petroleum Geology. He's a native of Billings, Montana. His degrees are from A&M and Mines, and he has experience in the industry as well. He's also served as president of several organizations, including APG, the Rocky Mountain Association of Geologists, and the Colorado Scientific Society. He's been involved on the Colorado Oil and Gas Commission and was the chair in the 99 to 2003 range. He's received a number of awards from both Mines and Texas A&M, from APG, the Rocky Mountain Association of Geologists, and honorary awards as memberships of all those. In addition, he received the Michael Halbilty Medal from APG. So the course that Steve teaches for SCA is a 3-day course that's offered in March in Houston, Texas. It's entitled Reservoir Characterization for Mudrock Reservoirs. So you can see the course description there includes several mudrock plays that will be covered throughout the course. So look for that. You can register to attend this class in March in Houston, or you can work with SCA to schedule Steve to teach this course in-house at your location and the time you wish. We have a number of webinars that we have scheduled upcoming, and we'll have Steve coming back at the end of February, giving an excerpt from another of his courses. And then we also have Jennifer Miskimmons and Raymond Woodward scheduled in March. So look for those upcoming webinars as we announce them. So I'd like to remind the audience today that you are muted throughout the webinar, and so if you have questions that you'd like to ask, you can use the webinar features to ask your questions by typing them in, and we'll cover those questions at the end of the presentation, and you will of course be anonymous, so here's your chance to ask those questions. Today's audience includes attendees from Canada, Indonesia, Malaysia, Nigeria, Norway, the UAE, and the UK, in addition to, of course, the United States. So without further ado, I'm going to give the presenting rights to Steve. And Steve, please start the presentation. Thank you.
So I'm assuming that presenting rights have been given over to me now, and
yes,
we'll go over. Oh, very good. Thank you. So we're going to go over a number of slides and cover a variety of topics about mudrock plays. what we think we know. So by the end, we will have hopefully covered off many of these bullet items. Obviously, in the time allowed, we're not going to cover all of this in any great detail, but we'll touch on all of these topics today. And I'm not going to, of course, read this list for you. One of the questions that always comes up about these kind of plays is what makes it unconventional to begin with. Generally in the mudrock types of plays, the quality of the reservoir is very tight. The type of trap that we deal with is what we refer to as a continuous petroleum accumulation, covers a large area. The lithology of the rock reservoir, the source bed is the reservoir, and oftentimes the state that the oil and gas is in, it can be sorb, tar, solid, or part of the bitumen still. Physical laws controlling the occurrence, the role of buoyancy is actually called into question, some other physical laws probably too. And then the viscosity and permeability also play a role in mudrock plays. Generally, we deal with something that is has moderate API gravity around 40, so our viscosity is good, but our permeabilities are quite low. The technology to extract, of course, is horizontal drilling and multi-stage fracking for these types of reservoirs. So a diagram that I put together, copying some of the similar ones from the USGS, illustrating in general where our mudrock reservoir plays are located, and that's in the bottom portion of the basin, and those reservoirs are either in the oil window or the gas window in many cases, and the oil window can be defined by vitrinite reflectance or Tmax values, as is illustrated on this slide. So we'll talk about those types of plays. In North America, mudrock plays are abundant and present in Mexico, the US, and the Canadian region. Of course, all starting in the US, and the amount of production associated with mudrock plays is substantial. So we'll not cover specific examples in the US today, but cover many of the topics that I illustrated on one of the previous slides. The impact on production in the US can be shown by this slide, where you can see that the overall oil production is at levels equal to the 1970s, and perhaps even above those 1970 levels. And that's all because of these tight oil or mudrock plays. We can also see what the EIA forecasts for tight oil and mudrock types of plays going out to 2040. And you can see from this slide where we currently are, our current production in the US actually is exceeding what the forecast is, but it's forecast that we'll be at the 10 million barrels a day production number, largely because of tight oil mudrock plays for the foreseeable future. We can look at also the gas production associated with mudrock plays, and one can see a dramatic increase in the overall gas production from 2006 to the present. And you can look at your favorite play out there and see how it is performing in regards to the other plays shown on the slide. We can also look at forecasts from the EIA going forward out to 2040, and the mudrock shale gas play is going to be the majority of the production for the gas. Tight gas still plays a significant role, but the shale gas systems, largely Marcellus, Utica, Haynesville, are going to be greatly increasing in the future according to this EIA forecast. So when you look at what constitutes success for one of these plays for mudrocks, there's a variety of factors that one can look at, and we can start by talking about the organic richness that the mudrock system has. We like to see those total organic carbon contents being 2.5 weight% or more. That has to be thermally mature, either in the oil or the gas window. Have to have a sufficient thickness of it. That all leads to what is our hydrocarbon in place. The mineralogy of the mudrock system should be dominated by a siliceous and a carbonate component and minor amounts of clay. That leads to the brittleness. The organic richness and maturation lead to, we think, pore pressure. So we believe in the concept of hydrocarbon maturation contributing to pore pressure. And then many of these mudrock systems have matrix permeability, but that can be enhanced by fractures that are present within the reservoir too. So all these factors then lead to the productivity of a mudrock system. It all starts with source beds, and the dominant type of source beds in mudrock systems that are successful in the US are type 2. Type 1 is successful in the Green River Formation. So it all starts with the right kind of source beds to begin with. When we look at the list of a sampling, and I've included one from South America in this list too, the Vaca Muerta. But if we look at this list, you'll see it's dominated by type 2. And of course, you could argue, well, there's a little type 3 thrown in, and that's a correct statement. But the dominant kerogen type is type 2 for all of these systems. And the beauty of a type 2 is it generates oil. And eventually, if you're looking for natural gas, you just look deeper in the basin where the oil then has been cracked to natural gas in those systems. So mudrocks, what are they? They're a very abundant sedimentary rock. 2/3 of them includes siltstones, claystones, mudstones, and shales. In outcrops, not very resistant. They're dominated by fine-grained material, clays and silt-sized material. And then we also have a variety of diagenetic events that occur within mudrock intervals. Clays change composition, and if we're dealing with biogenic silica, there's some transformation in the opal to quartz. We can look at a variety of diagrams which illustrate the overall sequences of mudrock systems as they're attached to shorelines and so on. And one could make the argument that whatever is happening at the shoreline is also represented out here in the deep basin. So we tend to believe in that. So the idea of sequence stratigraphy being applied to both areas, both the shallow sea settings and then also in these deeper marine settings. Of course, there's a whole variety of factors that control stratal patterns, and that is illustrated on the slide for you. So again, we're dealing with a class of very fine-grained rocks, and this particle size is 62 microns or 0.06 millimeters or less, dominantly in size. Where does all that mud come from? Kind of a diagram that I cobbled together that illustrates both lime mud and clay mud. We can erode a lot of things. We can also have clays come in from volcanic sources. We can also have biochemical precipitation and so on that then gives us these very fine-grained particles. So erosion or by some sort of a precipitation is how we end up with all these very fine grain sizes. A little diagram which then illustrates mudrock deposition. We are dealing with something that can be in a variety of water depths, anywhere from shelf to deeper water settings. The variety of biogenic participation in mudrocks can be from planktonic forams, biogenic carbonates, biogenic quartz. One component that we also like, of course, is some of those are very organic rich, but simple algae too. Oftentimes fecal pellets forming as a result of copepods or something else in the shallow waters contribute to these deposits at greater depth. we generally think of fair weather wave base as being about 20 meters and storm wave base 100 meters. So there's a variety of currents and such that can operate on the seafloor bottom, geostrophic to storm currents, and give us a variety of sedimentary structures. So a lot of things can come in from detrital sources into a basin, and then we can also have this biogenic contribution to the mudrocks as illustrated. So a ternary diagram which just illustrates how mudrocks can be, and a variety of authors have different ways to illustrate mudrocks, but this ternary diagram after Lazar illustrates how they can be subdivided into more argillaceous, siliceous, and calcareous types of systems. A lot of information on this slide, and time does not permit me to walk through some of the individual components. You can also look at, when we look at this classification of mudrocks, the clay, the quartz, the carbonate end members, but a fourth end member, of course, is that organic carbon component. And the type of systems that we like are these things that we would term as black shales, where the TOC content's greater than 2.5 weight%. If it's less than that, you're probably in this gray shale category, and it's probably not a very good clay or mudrock system to begin with. So the mudrock reservoirs, we have these siliciclastic mudrocks, the carbonate mudrocks. Sometimes we have additional horizons that are deposited with these units too. And we have both biogenic and detrital components to both the siliciclastics and the carbonate types of mudrock systems. And then some of the hybrid reservoirs would be something immediately adjacent to these organic rich intervals that can be a great contributor to production. So biogenic sediments, defined as having at least 30% skeletal remains, presently on Earth cover about 62% of the deep ocean, and we have calcareous and siliceous oozes. If we look at this diagram from Davies and Gorsline from the 1970s, it illustrates where we actually have deep sea clays versus calcareous sediments versus some of the siliceous sediments, and the siliceous sediments are both radiolaria rich and diatom rich intervals in this particular case. So abundant on Earth, and what we then explore for are similar situations in the ancient rock record. So the composition of recently deposited marine sediments, detrital comes from continental weathering, the biogenic created in the water column, the inorganic material created in the water column, the authigenic material, and so on. Under number 2 up here, quite important, I've highlighted one of the biogenic aspects of what's deposited out there is organic matter, and that's what we're interested in to make a good mudrock system. Carbonate oozes consist of tiny particles, mainly coccoliths, but also some forams. So we end up with a bimodal particle size distribution when we look at a lot of the carbonate oozes, also giving you a average rate of sedimentation that is thought to occur in these carbonate chalks and so on. Siliceous oozes have a variety of things within them, but can be largely diatoms and radiolaria, and also in this case giving you what the sedimentation rates are for the various siliceous oozes, as has been documented by a number of workers. The distribution and accumulation rate of production of biogenic particles is dependent on the nutrient supply and the temperature. Also can have dissolution of particles in the water column as they reach the bottom, so depth and chemistry plays a role. And then another factor that can occur to some systems is dilution by detrital or terrigenous types of sediments. We can look at then a diagram which illustrates what's our typical nutrients within the water column, which greatly contributes to the growth of all of our biogenic components of mud rocks. And then you can again see the things that could dilute these systems, clays and silts coming in from aeolian or hypo or hyperpycnal types of flows. We do a lot of XRF work on many of the mud rock systems, and that's why a lot of these elements then are named on as and where they come from on this particular slide. Organic richness, as has been published by Bohax and others, is equal to production minus destruction plus dilution. So a great diagram illustrating that production and the nutrients, and then what can be impacting that organic richness is destruction or dilution. We can look at average shale compositions on a ternary plot and this one adapted from Peter Scholl's plot, but end members of our ternary plot, clay, carbonate, quartz, feldspar, end members, and then we can also look at some of the better known mudrock successful plays on this particular diagram. And it's interesting to note perhaps that most of the Cretaceous plays end up plotting close to the carbonate end member, whereas Paleozoic and part of the Mesozoic ones are more in the siliceous or the siliciclastic end of the diagram. Changing topics, which I will do in our short visit today several times, but one of the aspects of mudrock systems is you are able to map out organic facies, and this particular diagram published from Davies et al. Just illustrates for the Mowry how it can be subdivided across the state of Wyoming into a number of facies: silty mudstone, graded siltstone mudstone, homogeneous mudstone, and way out here in the middle part of the basin, the radiolaria-rich mudstone. So that's typical of mudrock systems, this ability to map out organic facies. We can look at, we've been and will focus mainly on the North America areas, but these mudrocks are present throughout the world. We've seen a tremendous impact on production in North America from these things, and the remaining part of the world could see significant increases in production once exploration and production is switched over to these types of plays. We can also look at a diagram of just the stratigraphic distribution of mudrocks through time from Clemmy and Olmashek, and it doesn't matter what age that you're looking at, all of them work. In North America, we have significant ones from Devonian and Carboniferous, and then also Jurassic, Cretaceous, and Tertiary intervals. So all of these contribute both to oil and gas production. But just a diagram to illustrate that distribution through time of source rock intervals. Well, the kerogen type that you start with means what are you going to end up with as the producible hydrocarbon. And if you start out with a type 3, of course, that'll result in gas production. But if you start out with a type 1 or type 2 kerogen, then that can be in the oil window lead to oil production, and with deeper burial and conversion of oil to gas, cracking of that then can lead to wet gas and dry gas type of production. And again, the dominant type of kerogen that we see in North America or the US is the type 2 kerogen. So understanding the maturation and the temperature windows and where you want to be exploring in a basin, either the gas or the oil window, is quite important. On this particular diagram, I have combined type 1 and type 2s together, just illustrating this idea of oil eventually going to natural gas, and the very end product, some sort of pyrobitumen at the last stages. Changing to another topic, in many of these mudrock systems in the deeper parts of basins, the basins appear to be dehydrated, not much water that's produced out of there. Or if you fracture stimulate the horizon, a lot of that frac fluid does not come back. So it looks like those mudrock systems are imbibing a lot of the water. So where did all the water go? And so compaction, dewatering, hydrogenation of kerogen, oxygen getting converted to CO2, other reactions simply pushed out of the reservoir. Whatever the causes, the systems appear to be dehydrated, and we end up ultimately with pervasive hydrocarbon saturation, and it ends up being more of a mining system out there. So when we look at these types of systems, hydrocarbon pervasively saturated system, we're working on, as a lot of other people are working on, what is the nature of this upper seal right here, some sort of a diagenetic seal that keeps some of these hydrocarbons in, not all of them, because some of them do escape and then are able to go into the more conventional types of traps. One of the things that we've noted about many of the mudrock plays around the world is what we would describe as the inverted fluid system associated with these types of plays. And the up-dip seal, as proposed by Wayne Camp in the Eagle Ford anyway, is thought to be kind of a bitumen plug. And then as you go further down dip, the reservoir quality diminishes quite significantly. You go into the oil window, wet gas, dry gas types of windows. But the nature of this up-dip seal is that a carbonate cemented interval, or as Wayne has pointed out here, maybe more of a bitumen seal, and that's what we're tending to lean towards these days. So the examples of inverted fluid systems are everywhere, and this particular slide just illustrates some of the well-known ones: the Eagle Ford, the Austin Chalk, the Vaca Muerta, the Biogenic, the Barnett Shale, and the list could go on and on. One of the issues, of course, with mudrock systems is the pore sizes that we deal with are quite small, and then we deal with gas and oil production, but we have pore sizes that are either in the micro or nano types of pore ranges, so very small pore sizes. And back to our previous diagram on the inverted systems, if we look at what happens to some of that porosity then that's present up dip, maybe everything's plugged. Then we get into the oil window. Recent work by Laux and others illustrate that the types of porosity that we have is inter and intra particle porosity, and you can see what the various scales are, hopefully, on his diagrams. As we get further down dip and further degradation of the reservoir quality, we have continuation of the inter and intra particle porosity, but then we also have these organic matter pores that come into play, and the pore sizes are much smaller than what we had up here and more of the oil window. Get into this other topic of the forces of expulsion that we deal with in the deep parts of the basin. It's very different than the force of buoyancy. And this forces of expulsion creates overpressuring, can help drive that water out, help dehydrate the system, forces oil and condensate into very small pore spaces. And we think in many cases, if that pressure doesn't bleed off, you can exceed the fracture gradient of the rock, so create small extensional fractures associated with hydrocarbon generation. So the concept of that pressure-driven system was developed by Fred Meisner and illustrated and published by Chuck Spencer in the 1980s. Diagram just illustrates this conversion of kerogen to oil, to condensate, to gas, and that tremendous volume increase associated with increasing thermal metamorphism. And overpressuring is found in many basins in the Rocky Mountain region as a result of hydrocarbon generation. We can go back to older diagrams like Jim Momper's diagram, where he illustrates burial depth, pore pressure on this side of the diagram, the areas in which you're generating gas or oil, thermogenic or biogenically. And when we get into the deep basin, the main takeaway from Momper 1981 is this tremendous increases in pressure, which can exceed the geostatic gradient, exceed the fracture gradient of the rock. And again, these little spikes right here from Momper's diagram would be where you're creating some micro fractures. It's an episodic hydrocarbon generation fracturing. And so you see a variety of these spikes associated with generation and then fluid release, lowering the pressure, and pressure builds back up and so on. And so this concept has been around for a long time of microfracturing. Tissot and Welty, Ungerer, Jim Momper's work. And this diagram just illustrating again the conversion of kerogen to bitumen and oil, and that resulting in some of the microfractures, and eventually, if you run into some other fracture systems, perhaps migration. Switching gears a little bit, again, one of the aspects of mudrocks that make them interesting is they have a variety of geomechanical properties, and we can look at geomechanical properties static or dynamically, and with logs and dipole sonic logs, we can use formulas to calculate Young's modulus and Poisson's ratio, which essentially are stiffness and squishiness, if I can use those terms, and that divided by that equals then what we term as brittleness. And of course, we're interested in rocks that are the more brittle ones, not the more ductile ones in many of these types of plays. So one of Roger Slat's slides, which illustrates this concept of brittleness and using measurements of Young's modulus and Poisson's ratio, is illustrated for you. He also looks at XRD data, and if you come up with a brittleness index and use a formula which is illustrated for you, these minerals divided by all of these components, ending up then with what would be your brittleness. If you combine that with the Poisson's ratio Young's modulus plot, you can see where ductile rocks plot versus where brittle rocks plot on this particular diagram. So that kind of understanding is critical for where you want to be landing laterals and which zones that you want to hydraulically fracture, stimulate, and so on. An understanding of the fracture systems that are out there. Fracturing occurs in a variety of ways, and time does not permit me to discuss all of those ways, but one of the types of fractures that are present in just about every basin around the world are these regional fracture systems, as have been described by John Lorenz and others. And this slide just illustrates a study that was done in the southern, or in the Powder River Basin a number of years ago by Parks and Gale. And it's interesting that the regional fracture systems were documented a number of ways. One by the orientation of the overthrust belt, predicted orientation is a Lawback diagram from 1992. They also had some oriented or some borehole breakout information. They also had some liniment work, also had fracture strike from image logs, all of which all agreed that the regional fracture systems were trending northeast across the area. So Vastar, in days gone by, drilled all their wells in this northwest to southeast direction. So it's just an illustration of the importance of regional fractures and how you would orient your wells in one of these plays. And this area in the Powder River Basin right now is a sweet spot area. Back in the 1990s, technology did not exist to make this a commercially viable area, but right now Chesapeake and others, this is their sweet spot area in the Powder River Basin. Switching gears one more time about the reservoir drive in these systems, If we're dealing dominantly with a gas reservoir, then that's a gas expansion type of drive. If we're dealing with an oil reservoir, it's solution gas or depletion drive is our drive mechanism for getting that oil or gas to the wellbore. The technology that's used then for exploiting these plays is one that is horizontal drilling and multi-stage hydraulic fracturing. And my little cartoon right here just illustrates 6 frac stages, and in many cases in North America now, that number of frac stages is more than 40 frac stages. And why is that important? Well, your Mudrock system itself then, and the wellbore, how much of that rock is exposed to the wellbore is dramatically increased over just simple vertical well drilling, as has been done in the past. So a diagram which perhaps is extremely difficult to read, but one in which we tried to combine all the attributes of the historic shale plays together, and even one from South America here on my far right-hand side, the Vaca Muerta. So any of your favorite plays perhaps up here, and then all the various attributes associated with those plays. And you could look at it and go, they have some similarities and then some strong differences amongst those plays. And to summarize some of the similarities and not make you read that diagram in any great detail, what are some of the key takeaways and suggestions? Well, total organic carbon content greater than 2.5 weight percent. Kerogen type, dominantly type 2. We have one of those plays out there that's in the Green River of the Uinta Basin that's a type 1, but everybody else is a type 2 and very minor component of maybe type 3 thrown in, but it's dominantly type 2. It's thermogenic accumulations. We're either in the oil window or the gas window. Some mudrock plays can have a biogenic gas component to them, so that can happen, but the vast majority of them are thermogenic in origin. Clay content matters, so having less than 40% clay and then 60% plus percent calcareous or siliceous components, quite important too. Overpressuring is a good thing to have within your system, and that greatly contributes to the overall economics of the play and the estimated ultimate recoveries within some of the wells. Overall systems should be a minimum of 50 feet in thickness, and many of them are even much greater than that. So those are some of the takeaways from that previous diagram. What wasn't shown on the previous diagram is just one of these notions that I did show you a couple slides ago, just this concept of what is the regional stress field? What is my SH max direction? What is the orientation of the well that we want to be drilling within some of these plays? So I offer up an unconventional continuous type of checklist. If you were trying to find one of these systems somewhere else around the world, what are some of the things that you might be looking for? And just rapidly going through some of this: pervasive hydrocarbon accumulation, buoyancy probably doesn't play a big role, abnormally pressured, generally we think mainly of the high overpressuring, lack water. We do have water up depth, and we have these inverted fluid systems. We do have low porosities, low permeabilities. We can deal with multiple or single layers of rocks. Natural fractures can help overall the productivity. Most of these systems are associated with mature source rocks. We can have some of them that produce some gas biogenically too. Hydrocarbons are mainly then of thermal origin. The fields have fuzzy boundaries in the deep parts of the basin and generally merge together after time. We've talked about these inverted petroleum systems. For a lot of these systems to work, some of our observations as of late, having something that's relatively tectonically quiet, not highly faulted, is important, and that keeps a lot of the hydrocarbons in place. If it's too faulted and fractured, some of those hydrocarbons were generated, but much of that then can migrate into shallower horizons. We think having a gas oil ratio of 1,000 or greater is also good, because that's giving you the energy of being able to produce the oil into the wellbore. And then the last one that we just have added to the list, many areas where Mudrock system plays work, you already had historically excellent conventional systems that were present. So one of the keys to having a good unconventional system may be having a good conventional system within that basin that you're looking at. So time does not permit me to show you exact examples from around the world or from the US for that matter, South America, but they are plentiful. So the summary on these systems, overall, Mudrocks are game changers for the petroleum industry. We've seen an unbelievable increase in both oil and gas production associated with these systems in the US, to where we are at now record levels. Technology does play a key role at the horizontal drilling and multi-stage hydraulic fracturing, and both the oil and gas systems, depending on where you are and what you're looking for, are also extremely successful in the US. So with that, I want to thank you for your participation today, and I'll be happy to answer any questions.
Great. Thanks, Steve. We're now open to questions from the audience. I want to remind you that you can type those in the webinar question feature. Later today, you'll receive a link to today's recording of the webinar. You can share that with your colleagues. You'll get an evaluation form, a link to the registration details for the class that Steve teaches for SCA Reservoir Characterization for Mudrock Reservoirs. That's scheduled in March in Houston. And one of the first comments we received from the audience is that when I was listing some of the countries that were participating, I left off Myanmar. So I'd like to give a shout out to Myanmar. They're on the phone with us today. So welcome all of you from around the world. So please give us some of your questions as we go forth. Steve, one of the first questions, you talked about the importance on your last slide of having that a historic infrastructure from conventional petroleum systems already in place. Why do you feel like that has such importance, and why have you added that to your list, your checklist?
It's not the infrastructure so much as having conventional fields that are already present within the basin. So I guess the side of that would be having an infrastructure, but the key to having a lot of these successful plays is you already knew there was a lot of oil and gas in conventional systems in that particular basin, at least in the US. And so it's just a hint that you can also then have a excellent, perhaps unconventional system deeper in the basin. So these is just a checklist. You don't have to have all of these present to make the basin work, but to having 80% of those present probably will be a step in the right direction.
Great. So we have another question. Could you go into more detail about what causes the inversion in these reservoirs, the Wayne Camp model?
So that overall, what we call the inverted petroleum system or fluid system, again, you up dip, you have water, and then that's when a high quality reservoir. Then as you go further down dip, because of increasing temperature and depth of burial, we have chemical and compactional effects that affect the reservoir, so a degradation of the reservoir quality with time. So we know diagenesis works, always has, and the reservoir quality diminishes tremendously. And so what we can illustrate is the presence of these systems. It was probably first recognized by a couple of different people in the Austin Chalk back to the 1990s, where water was recognized up dip, and then the oil window, and then further down dip with a diminishment of reservoir quality, they found natural gas. So Berg and Hines, and then Larry Meckel also in some of his work in 1993 illustrated this idea of the inverted petroleum system. And so one of the questions that comes up is what traps the oil and gas in the deeper parts of the basin to begin with. And that was what was shown on the Wayne Camp model is the first thing that you generate from the conversion of kerogen to hydrocarbons is bitumen. And so you can have an up-dip bitumen seal associated with where you were actually generating hydrocarbons, and that helps trap the hydrocarbons then into the deeper basin. You can also do it with diagenetic carbonate seals, and then so the work that we're doing is trying to determine are both of them operative, just one of them operative. In the past, the John Masters model for trapping hydrocarbons in the deep basin was more of a water block phenomena. So up dip water, down dip hydrocarbons, but just the clogging of the pore systems, the smaller pore systems by water. That's the third way to trap some of these things is by a water block mechanism. So do we know exactly which one it is? No, but there's enough information in Wayne Camp's presented some information and all the SEM pictures which illustrate this up-dip bitumen seal. So we like that model that Wayne's come up with.
Great. Here's our next question. Do you think that overpressure may play a role in the preservation of liquids that might otherwise crack in an open system? And do you think overpressure retards maturation and especially the gas formation?
Well, again, our overpressuring kind of depends. There's, of course, 10 or so different ways to create overpressuring in reservoirs. But a lot of the systems that we look at, the hydrocarbon generation is the thing that is actually creating the overpressuring to begin with. And so with time, the first thing in a type 2 kerogen source rock, the first thing you generate is going to be bitumen, and that goes to oil. And then if that's buried deeply enough, that oil then will crack to natural gas. And the volume expansion associated with that oil to natural gas, it's a tremendous volume increase. And again, that's going to contribute to overpressuring once again within the system. So I have to be a little careful how I answer that question because I'm more in a hydrocarbon driven overpressuring discussion in my brief presentation today. And there are other ways to create overpressuring in basins in addition to the hydrocarbon generation. So hydrocarbon generation and then that conversion with increasing temperature and burial depth can result in great overpressuring at depth.
Next question, what are your thoughts about heat flow importance in the basin affecting the shale plays?
One thing that we've noticed, and there's only so many topics I could cover in my 40 minutes today,
right?
But that would have been another one of the topics that I would have covered. And if we ever do this again, I probably will. But we think heat flow is a very important component to sedimentary basins. And some of our areas in the Rocky Mountain region, one of the first things that we do is actually try to map out what the various geothermal gradients are across the basin. It's not uniform in the deep basin. We have a tremendous field in the Denver Basin, northeast of where I'm located here in Golden, the Wattenberg field, that's associated with a big temperature anomaly. And why do all the Mudrock systems work in that particular area? it's because of the thermal anomaly. And so understanding geothermal gradients and geothermal anomalies, I think, are key to helping you find these things that we call the production sweet spots in the deeper parts of the basin.
Okay, the next question from our audience: how do you know if source rocks are either actively generating or have recently ceased generation in petroleum systems modeling?
So part of the answer to that was part of the question. And so looking at the systems themselves, trying to understand what are the pressures that we actively see within those systems, and then actually doing the modeling on the various systems too, to see, are they still, as the saying goes, in the oven, or have we, has a system has a region undergone uplift, a pyrogenic uplift or something, so those source beds are no longer in the oven. And so trying to understand all that involves some careful work, seeing where fluid contacts are and so on. And the Rocky Mountain region is an area where we have tremendous epyrogenic uplifted associated with some of our sedimentary basins. And that has most definitely impacted areas that were generating hydrocarbons 40 to 60 million years ago, and maybe those source beds are no longer in the cooking pot, or they are in the upper part of still in the oven, but the temperatures have gone down. So that's an excellent question, and one can get at that answer by a variety of avenues, but one of them would be most definitely thorough basin modeling of the area that you're dealing with.
Okay, so the next question is rather detailed, so I'll attempt to summarize. The setting is the Delaware Basin. We're talking about the Avalon Shale, and there was a reference to a talk at ERTEC about how the Avalon has an RSBO in the oil window as measured from core. And so the question is, how is the Avalon in the oil window? And then at 25,000 feet deeper, the Wolfcamp is also in the oil window. The questioner asks, the RSBO with depth would make me think it should be gas. So what's the point at which it gets cooked enough to become gas? And what causes that?
So not seeing those data, but would love to see them. So anybody can send me an email or send it to Susan, and then she'll send it to me. Would love to see that, but again, you can have areas of the basin at great depth that have never seen tremendous temperatures. And so that R sub O of 0.8 or 1.0 or whatever it might be is something to examine. The other thing to examine is we generally measure the thermal maturity in many of these mudrock systems a variety of ways, but using source rock analysis and Tmax numbers and or the R sub O types of values. So one has to be a little bit careful in determining how mature systems are, one, and then do you have enough vitrinite in the rocks to begin with to actually have given a proper value for the thermal maturity. So that'd be number two. And then number three, things change in areas of the basin quite significantly. And so you can be at great depth and still be in the oil window because it's just never, it's not at the high temperatures as elsewhere, perhaps in the basin. That gets back to one of the previous questions about just the geothermal gradients across a basin can change quite dramatically. So great question. Would love to see those data and would like to work on that problem.
Yeah, it does sound like some of it's been published, so that's good.
Yep.
Next question, even though permeability is induced by hydraulic fractures, how important is the matrix permeability in mudrock reservoirs?
So another excellent question, and I think when we've looked at a lot of these systems, the idea that they don't have any matrix contribution is probably not correct. So with all the work that's being done with scanning electron microscope, illustrations of pore systems, which mainly focuses on the matrix contribution, that's been illustrated in many of these systems. And so from the inter kind of particle porosity, as has been talked about by Laux and others, to the organic matter type of porosity that's a much smaller scale, but that's all something that's within that matrix system. And then in addition to that, you can have natural fracture systems that are present. And then in addition to that, the artificial hydraulic fracturing and the frac stages and the increased volumes of proppant and so on, great advances in technology, all are essentially creating an extensive fracture system that enables these things to work. So in general, we view these, many of these systems as being dual, to kind of get to the answer, dual porosity, permeability systems, both matrix and fracturing, contributing to the overall production. So we don't generally like to think of them as having both. So it's present.
The next question is really in two parts. Would you say that brittle mud rock is often localized within a basin, and is this often related to a sweet spot in an overpressure area?
So again, the brittleness just has to do with, part of it's the mineralogy of the system. And again, the overpressuring aspects of things can help create, depending on the amount of overpressuring, can help create some fracturing within those mudrock intervals. So having the right type of system and then just understanding some of the changes that we see within the deep mudrock intervals is important. One of the first slides that I illustrated was, which we'll talk about in the course, but just to hit on a little bit, is what are the changes do we see within the systems themselves? And we see lots of what Roger Slatt would term little gamma ray cycles within a lot of these mudrock intervals. So more clay rich to more non-clay rich kind of little cycles. And that gives us these little brittle ductile couplets. And so trying to understand brittle ductile couplets, the thicknesses of those couplets, and overall where do you want to be landing a lateral within those systems is all quite important. So it's a whole combination of things that one has to look at, and probably not one simple answer to that question.
We have a few questions that we won't have time to get to today, so Steve will provide those to you so we can answer them via email offline. We thank you for everyone's time and attention today. This has been a very interactive webinar. We've had a lot of questions from our audience, and I'll remind everyone that after we close today, you'll receive a link to the recording of the webinar, an evaluation form, registration details for the class that Dr. Sonnenberg teaches in March in Houston, entitled Reservoir Characterization for Mudrock Reservoirs. Thanks, and we'll see you soon. Bye.
Thank you all.